This is section 5.9, building models from data. It is the last section of the chapter. You absolutely need your calculator for this lesson, and your book is super helpful as well. So before we get started, I want to look at what is called R squared, which is known as the correlation coefficient. It is known as the correlation coefficient, also known as the coefficient of determination. What it's going to tell us is how closely related are the data points to the regression. We want the data points and the regression to be as closely related as possible, meaning like 100%. I want R squared to be 1. The closer to 1 or -1. 1 would be a positive correlation. -1 would be a negative correlation. The closer I can get R squared to 1, the better that means my model fits the data. Where does the model come from? The model comes from your calculator. So if you remember the problem on the midterm where you had to do the candy bars, and I asked you which regression fit better, and it was clearly a quadratic regression, R squared helps you determine that. You didn't need to know it for the first midterm, but I will show it to you now. So I just happen to have this graph in my calculator, and you can see that, in the beginning here, this regression really fits the data nicely. But as I go up and up and up, this happens to be a power regression, it does not fit my data at all. The data actually happens to be logistic. So what's this R squared and where does it show up? Mode. So on your calculator, go to mode. And then arrow down to stat diagnostics. And you can see mine are turned on. So you're going to want to turn those on. Okay. So now when you do a regression of best fit, whether that be linear or quadratic, or what we're going to talk about today are exponential, etc., R squared will show up and will help you determine how good is this equation. Okay, stat calculate. Once you have your data in the calculator, you can do a linear regression, a quadratic regression, a cubic regression, a quartic, an inverse linear regression, natural log, exponential, power, logistic, sine. Okay, so you plug in the data and how you find the regression is all the same. It's just a matter of which number do you choose? Do you choose 6 for cubic? Do you choose 9 for linear, etc.? And we will talk more about the correlation coefficient as we're doing some examples. Okay, so right now you should look at number 2 in the problem set, which is on page 339. So pause the video and type in the data for 339, number 2. Okay, so we have stat, edit, and there is all the data put in. So the problem asks you to draw a scatter diagram. So make sure your plot is turned on. So my plot is turned on. So I'm going to do a zoom 9. Make sure your plot's on. A zoom 9, and there is all the data. Great. I'm not concerned that you actually draw that on your paper. That's not a problem. It says build an exponential model. Okay, so I'm going to do stat, calculate, exponential, which is actually 0. Okay, so depending on your lists, I always keep things in list 1, list 2 for the most part. Store your regression equation, alpha, trace, store it wherever you want, y1, y2, whatever. And now When you calculate the regression, you'll see that it has r squared, and r squared is 0.96. We don't care about r, we care about r squared. So r squared is 0.96. That, you would think that's pretty good, but believe me, we have built regressions and we will build regressions that are 0.99. So I'm not upset with 0.96, we'll take it. So we're gonna have y equals a, which is 1.6, we'll do 6.1, times b, which is 1.21 to the x. So there is our exponential regression. And then I don't think it asks me, but I'm going to write down that r squared is 0.96. So that means that there's a 96% relationship, positive relationship between the data and the exponential regression. Okay, you see on your calculator, and this is how I think I mentioned in the last video, it says y equals a times b to the x. Great, that's what we just did. Y equals ab to the x. But you also notice though that all the problems in section 5.8 and this one as well, it says express it in the form a of t equals a sub 0 e to the kt. So I need to turn this y equals ab to the x equation into one of the form with a base of e. All right, so here we go. A sub 0 represents the initial amount. But isn't that what A represents here? A also represents the initial amount. So A sub 0 is the same as A in the two equations. Okay. Y, A of t, this gives you the amount of whatever it is, people, fruit flies, bacteria. This is the end amount that you get after you plug in for t. Okay, well t, x represents time in y equals ab to the x. And t represents time. Okay, oops. So you end up with b to the x equals e to the kt. Okay, so a sub 0 are the same. We have our base, which is b. Here we have our base, which is e, to the x, to the kt. Raised to the x, raised to the kt. But x is the same as t, which I just determined right over here. They both represent time. So you end up with b is equal to e to the k. The base in exponential form is the same as e to the k in growth form or decay form, whichever one it is. Okay, so now we can solve, and we know that the base was 1.21. It was more than that. It was, I didn't write down the whole thing. Yeah, I do still have it in my calculator. I happen to still have it. 1.208. 263,492. It's okay if you don't have that. I just got lucky. Equals e to the k. All right. Solve for k, and you get about 0.1892. Plug into your calculator. The natural log of 1.208, blah, 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 blah. It's 0.1892. So exponential form, and I honestly don't know what this name of this form is. I don't know if they call it growth form, decay form, whichever. I mean, it is exponential of a of a sort, but here the base is B and here the base is E. So I don't really know exactly what name they give. I think they call it the growth model. So this is going to be A of T equals 1.61 E to the K, which we just found out was I'm just going to say 0.19 T. We are asked to graph the function. I always just do a zoom 9 to make sure I'm there. Look at that. Look at how closely related those data points are. You know what? This is the same graph I showed you before. Sorry. All right. The next question asks you to predict the amount of ethanol that will be produced in 2015. Okay. So according to what we've plugged in, the year 2015 is when X equals 15. So you can just do a quick table. Second table, I'm gonna start my table at 15. And 27.492. Okay, and I don't know, what are we? Billions of gallons, holy guacamole. Okay. Okay, so you know how to plug into the calculator. It really is just a matter of being able to plot things correctly. This is the key right here, what I did, knowing how to convert it from exponential to the growth or decay model, depending on the data. Let's take a look at number 8. The data for number 8 is very similar to the data for number 2 in that it's years. So that should save you some time when you are trying to plug in. Number 8. Pause the video and put your data in your calculator. If you haven't already done so, pause the video and go ahead and take care of your logistic regression. No R squared for logistic. It has asymptotes. The logistic model has asymptotes, and so the data is approaching either the carrying capacity or it's approaching 0. There is no R squared value for logistic models. Okay, so the great thing about all of the regressions on the calculator is that they give you the generic formula to start with, and then really all you need to do is plug in. So if we create our logistic model, that is going to be y equals C, which is 15.34, I'm going to not abbreviate, round, over 1 plus A, which is 1.52, E to the negative BX. Okay, so B is 0.02, so it's going to be negative 0.02x. So this is actually growth. You have to be really careful about that. This is actually growth because it's E to the negative BX. Right? And you guys are so used to saying negative B, but if you've had me before, I never say negative. I always say opposite. So it's the opposite of negative 0.02, which is positive 0.02. So this is actually growth. So predict when the population is going to, the population in 2020. Well, let's draw a graph first. It doesn't look logistic at all to me. It looks like a line if you ask me, but it is indeed logistic. It is indeed logistic. Sometimes it's really hard to tell, but that's why we have regressions or the calculator to help us figure it out. So they want to know in the year 2020. So hopefully you did too. I did my years from the year 2001. So I had that represent 1. So the year 2020, which would be 20, I'm just going to second table. $7.65 billion. So in the year 2020, we expect the population is going to be 7.65 billion. That is a lot of people. Okay, and then it says, when will the population be 10 billion? When will the population be 10 billion? So this is when your y, so when your y equals, and type in 10, draw your graph. Oh, it doesn't look like they intersect. So when I did a zoom stat, this is what it looks like. And my y equals 10 isn't even showing up. So again, I did a zoom stat. It's working slowly. It looks like the data fits perfectly. So I'm going to look at my window. And if you notice, my y max only goes to 7.2581. But if I want to know what it's going to look like when y is 10, I'm going to change this to 11 just to give me some room. And it should show up. Okay, so I paused the video and I played around with my calculator, and here's what happened. So here's my zoom stat. Great. And I wanted to know, when's the population going to be 10 billion? So my Y2, I typed in 10. And so then we can see where the two lines intersect. And at first it didn't show up at all. So then I went to my window. And this was the window that you get when you do the zoom stat. And so I thought, okay, well, if you look, if I want to know when the population is going to be 10 billion, then my Y should be at least 10. And according to this window, it's only 7.2581. So I thought, okay, I'm going to put it at 11 and let's see the graph. Okay, and you wait and you wait and you wait. And there's Y is 10 and they still don't intersect. And I thought, okay, maybe this doesn't work. But I know it has to because the carrying capacity is 15.34. But on the logistic model, the carrying capacity was 15.34. So clearly 10 billion is less than 15.34. You know, what the heck's the problem? So then I thought, okay, let me just check the table. Maybe it just doesn't work. And when I check the table, clearly, if you scroll down, you can clearly see that Y does, the Y1, my logistic model, there it is. It definitely reaches 10. So how come I can't see it on my, how come I can't see it on the viewing screen? So I'm back to the window and I thought, okay, something's not right here. So I changed my X to 0 because we're starting at, what do you call it? The N sub 0, the first year that we're doing this was 2001, which represented 1 on my scale on my viewing screen. So it makes no sense though to have any negative years. Great. So then I thought, okay, let's just change this to 20 and see what that looks like and go by 2s. And I'm going to do Y, same thing. And I'm going to go from 0 to at least 10, right? Because that's the problem's asking me to do 10. But I know the carrying capacity is 15. So I moved it to 16. Make sure I can get a good view of it. And I graphed it. Okay, good. I'm getting closer. And so let it graph, and I still can't see it. So you may have tricks that I would love to hear. For me, I just had to play around with the window and I said, okay, gosh darn it, it's way down here somewhere. So I just said, okay, forget that. I'm just going to go from 0 to 100 by tens. And if it doesn't show up now, I don't know what I'm going to do. And it indeed does. So now I'm just going to do my second trace intersection, enter, and it is 50.6. Again, I did second trace intersect, and it's 50.6. So it's around the year 2050 to 2051. You know, another thing you could have done is, you know, you get to the table, and I think earlier I scrolled down and I was saying, okay, I know it reaches 10, and it looks like it does that around when X is 51. So you could have adjusted your window based on the table. So that one, you know, was a little bit of trickery on the calculator, but they did indeed intersect. And another way that you know that is, let's go back. The carrying capacity is 15.34. You were asked to find, when will the population be 10 billion? That fits. So if you were asked, when will the population be, you know, 20 billion, you would say, well, the carrying capacity of the world, or whatever it is. Are we looking at the world, or are we looking at the US? Yeah, the world population. Then you would have to explain, well, it's outside of the carrying capacity. It never will reach that amount, et cetera, et cetera. That is the end of chapter 5.